very quickly going over the combination circuit and the parallel circuit to that. One of the things that we have to make connections as electricians. I mean, we don't study stuff in a vacuum. It's kind of taken holistically. When you are working on a circuit, you may be called upon to troubleshoot a circuit. And my power supply wasn't plugged in. At any rate, you may be called upon to troubleshoot a circuit. And if you understand the theory behind it, you may be able to quickly figure out where the problem in the circuit lies. Even as something as you walk into an office building and they've got fluorescent lights, well, they wouldn't be fluorescent anymore, the LED, but they've got a bank of lights and one of them's not working or the circuit keeps tripping, and you're trying to isolate where that might be. Well, to understand where the differences are in the circuit as you change it, as you make either deliberate changes or accidental changes, that will help guide you to quickly figure out through process of elimination and other things which particular fixture is causing the circuit breaker to trip. And all of that is predicated on knowing how to use your meter and how to analyze a circuit. When engineers design buildings, and I did not take any engineering, but prior to my becoming an apprentice, I used to be an estimator. And if I wanted to change the loading on any circuit because it was advantageous for wiring and it would save us money, I would have to write out all kinds of letters and get everything stamped and approved and signed off because of the loading. It wasn't my job as an estimator and purchaser. It was not my job to go through and do all the math. It was the engineer's job. And if I came up with a solution that might save us money, they might turn around and say, no, you can't do that. And they would have a rational reason, or they wouldn't. And it's entirely up to them. But as I got into my apprenticeship and I actually started learning the theory behind it, a lot of it started to come back and go, that actually makes sense. Now I know I couldn't do that. Okay, all right. Because, to save a nickel or a dime there, if it makes the entire system unstable, you haven't saved anything. You just save some money now to pay for problems later. And it might not even be approved. So at any rate, let's carry on. I've got to say a few things I want to go over. Some of these are like multiple choice and somebody can speak up and see if they have the answer for us. So moving right along. Oh, of course, now it's not going to work. Really? Honestly, I get. I don't have my second monitor. You've got to be kidding me. You are sharing another application. Stop sharing. Okay. Gotta turn my camera off, I guess.
So is this test going to be in person?
What's that?
Is this midterm?
Yes, it's a written exam. There's two different versions. They're already printed off. There'll be dividers up. Make sure you bring a couple of writing utensils in case your pencil breaks. Make sure you bring a calculator. Phones will not be allowed to be used to do calculations. So if you don't own a calculator, I would strongly recommend you go out and procure one. I think they're all of $4 at the dollar store now, a Dollarama. But yeah, you can't bring your phone.
The good ones are the scientific ones?
I'm sorry?
It's like $10 for the scientific ones?
Last time for what we're doing here, like I've gone out literally when I forgot my calculator at my place up north, and I just go to Dollarama, and the one they have, it's hang on a sec. I think this was all of $4, and it does 1/x. It's got log. It's got like everything you're going to need. If you need more than this, like if you need grafting, sure, okay, we'll get a grafting one. But for just quick calculations, this will do it. We're not getting any Fournier calculations or None of that stuff. So it's like for $4. That's what I paid for it. And it was about 2 months ago. So cheaper than the gas to go and recover it. I'm going to see if I can get this thing to work. Okay, now I'll see if I can get can you see the PowerPoint now?
No, Professor, we are not able to see.
Oh, perfect. I don't know why they have to, they switch us over to Teams. It was so easy before. Now, give me a sec, I guess I have to log in a second time, I guess. Just mind-boggling. Can't do that even. It's not just dandy. And okay, let's see if I can share it on this one. Okay, can you see it now?
Yes, Professor.
Wow. That's more than a thing. And I have a belief, well, now it won't let me change, stop sharing the screen. They won't let me do anything with it. Really? It's a fixed screen. Perfect. Oh, that's just getting better and better. Can't get out of it. Now it's unlocked up. I really don't know how Microsoft stays in business. Nothing, like, I'm not going to go there. I'm just going to get very annoyed.
Xbox is keeping them afloat.
Oh. Yeah, okay, that works. We'll go with that. Okay, I don't know if I'm going to be able to do this as well, but we'll. No, it's lost all its functionality. Okay, I can do that. Okay, I can't make that disappear anymore. Nothing seems to want to do anything that I should be able to do. I just. Okay, so the other solution is I'd have to go get my other laptop this is beyond the pale. I'm following the instructions I was given by Copilot as to, oh, you can just do this, and apparently they lied. It's not the screen I want to share. Okay, the other join. I thought I was already joined. No, I don't want to do that. Can't block. Ah, this is so stupid. Don't want to use that. Block. Block. Yeah, I know my turn. Got 4 reminders that I'm supposed to join the meeting. I'm in the meeting, and it's saying, do you want to join? I'm in the meeting, but no, I'm not in the meeting, apparently. I don't use, turn off, don't join now. Oh, yeah.
What the fuck just happened, bro?
Bro, it sounded like someone was trying to play us hot cross buns on their recorder.
Wait, what's going on? I just woke up.
I don't know. We're having technical difficulties at the moment. The teacher despawned because he had another microphone next to another microphone, and it was doing that like annoying echo.
Yo, is it online or is it in person? You keep saying something about calculators.
It's in
Oh, is it
person.
in person?
Because for our
Tomorrow.
exam, I'm pretty sure we're doing our exam in person.
Oh, it's in person now?
Yeah.
For the exam, I'm pretty sure that's what he told us. It was going to be in person.
Yeah.
This guy's good.
He was saying it was online.
Wait, you guys are doing it
I don't know.
online, or
Maybe for you guys it's online, but for us, he said that he was going to make it in person. So I'm not sure. He said that he
Wait,
was
Wait,
on
who's
the
who's
us?
fence
Which
about it.
class are you guys?
This is a written exam. Sent to all of
We're
us.
like Thursday's class.
It's
Oh,
in
no,
class.
Wednesday. So Wednesday is online, Thursday is in person?
I guess. I don't know. Like I said, I don't know what you guys are doing. All I know is he said that he finally made a decision.
person.
My instrumentation class is on Tuesday, so
I feel like he wouldn't make one online and the other in person, but that's just me.
That's so unfair, man.
That's what I was gonna say. I was like, what the fuck?
Okay, I'm
But
trying to
dude,
get my other laptop to work now, so I'll have to have 2 laptops going, I guess, if I can get in. This is like I never had an issue with the old bongo. Like just worked great. Pop, 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 change screens, a little pop up. I posted a video that went through that second circuit and compared it to the first circuit. Did anybody have a chance to watch that?
Yeah, I did.
Okay, because it lays it out exactly what you should have found through the process. Okay, then I'm going to do this. And this one I got to turn off my this, turn off my mic. Okay, hopefully you can see this. Okay, so there was a few things I wanted to go over with respect to the resistors and stuff. When you were working with the small resistors, some of them were larger and smaller, and we went through this, but there was a couple comments I got in feedback that didn't really make the connection between the amount of wattage or throughput power that a resistor can handle before it burns out. So basically, size matters with resistors. The larger they are, the more wattage they can handle. Now, we all know that current times resistance equals voltage. So if you increase the voltage, you're going to increase the current because the resistor is fixed. But the other part of that is that the greater the size, the more air circulates around it. The one that's shown here, it's got these little fins in it, and you can see it's bolted down to a board. So what that does is that the resistor itself, the current's going to flow through it, but this aluminum, and depending on what it's bolted to, will allow air to circulate to wick away some of that heat. And as it starts to wick away, if this screw, for example, is connected to the chassis, then the chassis then becomes an even larger heat sink to take that heat and soak it away from the circuit board itself, like from the actual resistor itself, so that it can handle the wattage that it's designed to have. So as a rule of thumb, each of these are set by a standard diameter. So a 1/4 watt is a very small one. That's the trying to think which particular resistor it was in your particular kit. The 100 ohm ones, large ones, they were rated for 2 watts. And the one I was handing out for soldering, they were a 1/4 watt, and the standard ones are usually 1 watt. You can also get them for 5 watt, and if you need more than that, then you get into the really large size. So there was the 1/8 watt, or 1/4 watt was the one I was handing out to do your soldering, so you wouldn't use up the other resistors. And the standard that you were using for the 100 ohm was 1 watt. As they get, these are all carbon base. The blue just as a reminder, it's not actually carbon. The blue one is usually a metal oxide tape that they use, and then they put it in a rosin, and it's a blue color. And they usually do that for this one's only a 4-band, but usually I find most of the 5-band resistors are the metal oxide, not the carbon. And then you get up to the ceramic, which is even bigger. They can handle more watts because there's more area to dissipate that heat. When you get into the really large one, this one here, it's got a lot of airspace, and it's hollow in the center. You can see they've got holes here. That's to allow for a chimneying effect to let air move through it, through convection. They'll use resistors of this size, and that's probably about 18 inches long. Okay, let me convert that to metric. So that would be 45 centimeters long. And they will often use those in dynamic braking. So dynamic braking, if you have like the streetcar or a subway, an electric train, electromotive shovels like in the mines, when you're driving it forward, it takes a lot of heat and generates a lot of heat. And what you can do is you can put that to work. When you dynamically brake, you're reversing the flow to get it to stop, but at the same time, you're using these resistors to dump a lot of heat as possible to use up that energy, and it helps to slow the vehicle down faster without having to rely strictly on brake shoes. That one you'll probably recognize from before. That's your typical electrical stove, and the one on the bottom is an electric hot water tank. If you ever get sent out to change a hot water tank element, it's a time-consuming task. And I used to rent my place up north. I used to have a lot of rust and lime sediment and stuff in the well water. I've since had it all treated, but I would go through a hot water tank in about 4 years. And I would call the company I was renting it from to come repair it. They would just send out 2 people with a new tank. That's how much time it takes. You've got to drain the tank right out, and then remove the heater element. It's usually the bottom one. Put it back in, start to fill it up, and then hope that it doesn't leak because you've got the gaskets right. Because if you get it more than half, the pressure will then blow by your gasket, and you got to drain it all again, put a new gasket, try again, and it can take you. I've actually had it when I went to, it took 6 hours to change the element just because of that leaking problem. Anyway, moving right along. Wire wound ones, I think I passed one of these around in class on not the one upstairs in the downstairs class. These are basically large potentiometers, and the wiper, it will put in a certain amount. They can take a great deal of heat. They're usually used in the old DC control for speeding up a motor. They're used in theatrical lighting. All these are heavy resistive loads. A lot of this, I will say, has changed because the theater lighting, for example, used to be incandescent and there'd be high wattage, but you could control the lighting for all the rest of it. But now they've gone to LEDs, so these will probably end up disappearing. Okay, so the other thing we talked about is a series circuit, and a series circuit not only currently has one path, but that one path, every single time you put a resistor on it, it consumes some energy. So there's a voltage drop. And every time there's a voltage drop, the rest of the circuit only gets what's left over. Now, if you have 2, 3, 4, 5 resistors of all the exact same resistance, and you have them in series, that then gives you the capability of making different voltages by selecting the 2 points. So in this particular diagram, if I were to put a load across one resistor, I would get 6 volts. If I put the load from the left to the far right, I would get 12 volts. And I think one of the questions that I asked on the series lab was, okay, you measured 3 resistors. They were all the same. You then put 2 of them, you measured across 2 of them, and you should have got about 8 volts. And then you measured across the remaining one, and you should have got 4 volts. The total applied being 12. So I then said, okay, well, if they're each 4 volts, and I got 12, what if I needed to have 3 volts? You could add another 100 ohm resistor, and then it changes the math, I grant you, but you then have 4. So 12 divided by 4 means that every resistor has a 3 volt voltage drop. And if you needed 8 volts, you might be a little out of luck because you're going to get 6. 8 might be happy with 6, it might not be. But you can use this, and they do this all the time. If you've ever opened up or ever do open up a desktop or an old desktop computer, you will actually find the power supply has multiple voltages on it because different parts of the circuit board require different voltages, both positive and negative. We didn't really get into negative flow and negative control, but there are circuits that do require a negative. When you get into transistors, you'll have sinking and sourcing, and that's one of the things that applies to transistors. Anyway, so a series circuit has 1 pathway for current to flow, 3 pathways. A series circuit has 1, 3, 2, or as many pathways for current to flow, and it's only 1 pathway for current to flow. So Kirchhoff's voltage law states A, that around any closed loop in electrical circuit, the sum of the voltage drops equal to the applied voltage. B, that the voltage in a circuit varies directly with resistance. C, that the voltage in the current circuit is directly proportional to the resistance and inversely proportional to the current. That that the product of all voltages is equal to sum. Product is actually multiplication. So the Kirchhoff's law, if this was the question that was stated, basically that around any closed loop in electrical circuit, the sum of the voltages is equal to the voltage, applied voltage. Just like I said with the voltage divider, if you add up all the voltage drops, you can account for every single volt. So which resistor in a series circuit receives the largest voltage drop? The one with the least resistance, the first, the last, or the one with the most resistance? And it's the one with the most resistance causes the greatest amount of current to attempt to go through it. The current will flow the most to the least, but the most opposition will give you the largest voltage drop. What is the total circuit resistance when a 5-watt resistance, a 25-watt resistance, and a 30-watt resistance is connected in series? Well, it's simply adding them all up because they're in series. 5 and 25 is 30, 30 and 30 gives us 60. So what is the symbol for milli or metric in the metric system? And it's just simply the M. The one beside it, I believe that's called the mu. You'll often see it because it's kind of an odd character. That's for microamps, micro ohms, microfarads, microvolts. You'll often see it as a type, especially in textbooks and stuff, where they can't have that symbol. They'll just use the letter U. So if you see UA, it does not mean United Artists. It means microamps or microfarads, etc. Parallel path has as many pathways for current to flow as there are loads connected in parallel. So you have 3 resistors and they're connected in series to a 120 volt source. The values of V1 and V3 are measured and found to be 42 volts and 8 volts respectively. So the value of V2 would be the 120 volts minus the 42 minus the 8, giving us 70 volts. Okay, Kirchhoff's current law states that the current entering any point in a circuit is equal to the current leaving that point. Now, when you're looking at a parallel circuit in residential commercial, anytime that you use a Moret, you're creating a node. Anytime that you're putting say a common into a terminal screw and then carrying on and you're jumping it, every one of those loads coming off that common or returning on that common is a node. You're dividing current. When you look at any amount of current going into any box, the amount of current going in will go somewhere. And it should go through a load. If you happen to open a live one and you represent a circuit, say through your fingers and your hand to the box and it completes the circuit, the current will flow through your hand and through the box. It'll complete the circuit. It current's like that. It's maliciously obedient. It follows all the laws of physics. So anytime you do that, you know that every single load, the current is dividing out as it works its way through the entire network. And at the other end, when it goes through the actual load, whether it's a LED light driver or whether it's an incandescent bulb, the neutral side is going to all be tied in and either at the moret or back at the panel. And all the current divisions that go out at every single node all get summed back in the node. So we have a 570,000 ohm resistor, and it may be designated as, this is where we're going to need our, remember our initials. So K is kilo, capital M is mega, small lowercase is milli, and that micro is that, I forget the name of that letter, it's a Greek letter, but anyway. So we take we reduce it down and get rid of the zeros. We had 3 zeros taken away, so that gives us a K for 1,000. So that's 570,000. Every time you do engineering standards, you have 3 before you get to the next division. That's why if you have a meter, you don't say, well, that meter is 1,000 centimeters, which it is, but it's also made up of 3 decimeters, which is 10 centimeters, or no, pardon me, 10 decimeters. We don't use those smaller ones. We do it in groups of 3, simply because it's easier to understand, and you wouldn't have to remember all the early ones in between hepta and I can't even remember that. Like, oh, there's millimeters, centimeters, decimeters, a meter, decameter, which is 10 meters, heptameter, which is 100 meters, and then kilometer. Well, they drop the deca and the hepta because we don't need them. We don't use them in common practice. Okay, which with resistance of 50, 100, 1.4, and 1 meg ohm in parallel, the total is only less than 50 ohms. So without doing the math, that question, the answer, you just save yourself a whole bunch of time because you know that it's the smallest resistance is going to be greater than the total resistance in a parallel circuit. And that's simply because you're dividing the current up. It's got more paths to flow and it still has the same potential pushing the electrons through the circuit. What is the amount of current flow in the circuit? So we have 120 volts divided by 15, and that gives us 7.46 amps. Because amps is the result of volts divided by resistance. The other thing that I found some of you are having difficulty with is getting used to reading the color bands on resistors. And this is strictly practice. If you want to use a way of remembering the order of the numbers from 0 to 9, better bring back racing. You're going to be very grumpy without it. That's the one I use. So it's better bring I'm trying to remember. Bring back racing, or you're gonna be very grumpy without it. Anyway, I actually we did the theory online, and it was during COVID, so nothing was happening, and I don't know why I got my NASCAR voice on, but I just kind of figured, well, we ain't got no racing now because of that COVID, And that actually literally popped into my head, and it actually makes sense. There are a bunch of them. You can go online if you want, and ask for the mnemonic, the way to remember the order of numbers, but whatever works for you. You're not going to have your color chart when you need it. There is some 3-band resistors that only have the 2, and then it has a gold, which tells you in that particular case that it's the tolerance. It skips over the rest of it. So on some precision ones, they don't need to tell you it's 1 times 1. They just leave the 2 bands and the actual the gold band. So on the 4th band and a 4-band resistor, there's a couple that you'll run into very odd times. Like they've got yellow, this is actually marked incorrectly. The 5% is gold, 10% is silver. Some of these other ones, you notice it's 0.5%. It's a very high standard. And I think that's this one that's plus or minus 5%. If memory serves me, yellow is NASA and orange is mil-spec. And it's not a matter of the tolerance, it's a matter of the reliability. I mean, yes, it can be a 100 ohm resistor, could be 105, and that in the application in the spaceship is fine, but they don't want that 100 ohm resistor to fail because, life support systems or, guidance or telemetry or any of the horrible things that can go wrong, you don't want it to be blamed on a single resistor that failed. When you're looking at them, and I find this method particularly annoying because they say there's a gap, and I don't know if there's some agency that's supposed to go around and measure the gap. I've had resistors and I've looked at them and I cannot discern the difference in the gap. So as I mentioned, when I set them up, I always try to put the tolerance band on the same orientation. So when I'm going back and checking my circuit, I'm not looking at it the wrong way, especially if you get into lighting conditions or you're all young and your eyesight's 20/20. When you get to be my age, I wear a high prescription in the first place. But the second thing is it's not the clarity, it's the light itself. One of the reasons I ended up retiring from doing the trade is a lot of the small number tags inside a control panel. I was getting, even with prescription reading glasses, with the lighting and the awkwardness of it, I'd have to literally stick my head inside a panel that I shouldn't be doing that. The second your eyesight can't be corrected, I haven't the desire at this point. I haven't been shoved into the desire, but at this point of actually having laser surgery. But I'm just simply saying it. If you look for the tolerance band first, it will flip things around for you to give you the correct order of, like we know that from this case, there's no violet color for tolerance under normal circumstances. So this would be violet, green, brown, black, and brown. And brown in this case on a precision one tells us that's 1%. So it's a 751 times 1 for a 751 ohm resistor plus or minus 1%. So if 35 volts was applied to these resistors, what is the current flow? So it's a simple series circuit. And we've got green, black, black, and gold, followed by brown, black, brown. And that's a 3-band, so it's got a plus or minus of 20%. And then we've got red, green, and brown. And all that together, and then divide it by our 35 volts, and you'll end up with 87.5 milliamps, or 0.0875. The other thing to keep in mind, especially when you're doing calculations, you've got to remember with milliamp, if it's not like 850 milliamps, you've got to put the 0 ahead of it and then put the decimal, because if you don't, what will happen is your calculation will be off by 1,000. If all the resistors shown had a silver fourth band and all were measured on the lowest end of their tolerance, what would the total resistance be? 37.5. So we have a 10% plus or minus, so we simply add the resistances up. And it looks like my picture got truncated, or you have to take the 210 volts divided by 5 to figure out what R1 was. And then after you have the total, you would then take that and multiply it by 0.9 for a discounting of 10%. And if you want to know the maximum, it would be the number times 1.1 or 110%. So what is the total resistance? I'm going to let you guys stew that one over and tell me what the total resistance is. Nobody wishes to take an educated guess or more accurately do the math. I'm saying how we've only got 10 minutes. So there is, yeah. I'm sorry if I jumped the gun there. We're down to about 10 minutes, so I want to get quite a few of this in if I can. Okay, so that'd be 12.7K ohms. I want to skip ahead on a couple of these. I'll leave this on Slate if you want to go through it on your own, because I wanted to go down to skip. Okay, so here's an example of what happens to the circuit if you start reorganizing the order of operation. So the original circuit is on the upper left. You had 33 ohms in parallel with then you have a 47 with a 51, 82, and 100. So you should have, in your calculations, came up with a number in around the 210 milliamps, that range. And then the current divided off through the rest of the circuit and straight down through the 33 ohm. And if you swap one out, so let's say that for argument's sake, I've got the circuit's kind of changed around here. You can see that the total milliamps that flows is completely dependent upon what's going on in the balance of the circuit. So the other circuit, I put the 100 ohm resistor first, then I put the 82, 51, and the 47 and the 33 were off on their own of the vinyl branch. And from 200 milliamps, we dropped down to only 95 milliamps. And you can see that the current flowing through all of these is now different. I didn't put all of the voltmeters. That's on that video that I posted. You can actually watch, and I talk it through how you do the collapse, and then you do the re-expansion, and then where all the currents go. The other thing to remember is that the software that I used to show these values, internally, it does what we don't do. We as don't want to remember 12 decimal places. We just want, okay, so it's 210 or 209.9. That'll be fine. That's close enough. Well, to the program, it goes, no. I take it as many decimal places as the 32-bit processor will allow, and then I multiply it. I do all the math with all the numbers. So some of the numbers you kind of look at and go, wow, that's more than I calculated. Oh, wow, that's quite a bit less. It's because of this, it can carry, and we don't normally do that. They're essentially correct, but there's going to be a slight variation on a theme. So the other thing I did was, in this particular demonstration, I also then took one of the resistors out of the circuit. And the one I picked in this case was the 51 ohm. And now what you have is 100 ohms in parallel with the 82, the 47 for 129, plus the 33, which is 162. So you end up with basically two, almost the same amount of current. I got 50 milliamps versus 30 milliamps. And it's simply because we opened up the circuit. So if you know the value that's going on in the first place, that would tell you just by measuring the current, and you've got a clamp-on meter to do it. Okay, all the loads are supposed to be the same. I've got light fixtures. Something's causing it to break out, or you want to find out, why one's not working. You could turn around and say, oh, okay. And if you analyzed your circuit and you knew where the joints were, you could actually work your way to it to find out where the open circuit is and why it's been dropped out. Just understanding Ohm's law and how the current is flowing will actually assist you in troubleshooting. Okay, so that's kind of, I didn't mean to rush all that, but I know you've got other classes, and I wanted to get through quite a bit of all that. You'll have the entire time on Tuesday and Wednesday to do the exam. There's no rush. It's not first in, first out the door. When you're finished, you'll let me know. I'll take your paper. Want to have your paper, then you're going to quietly leave. And then, as I say, they'll all be marked. All the marking will be caught up. If not the balance of this week, I know I owe you a lab still, then it'll be definitely for the first part of reading week. No later than, I would say, Tuesday of next week, you'll be caught up and you'll have all of your marks up until this point. I'm meeting with the other professor to explain exactly how far we've got during reading week. I think on the Tuesday we're meeting up. I'm going to go through, show him the book. If he wants to carry on with my book, that's entirely up to him. If he wants to go a different route, that's entirely up to him. He's competent. He's a good professor. So his style may be completely different than mine. That's to be expected, but the same course material will be covered. He'll know exactly where we've come up to our breaking point, and he'll carry you on for the balance. Are there any questions about the midterm moving ahead? Do we have an exam on lab day? Yes, that's the exam will be on lab day in the lab room, same bat time, same bat channel where you had it before. So it was either upstairs or it's on the main floor. But yes, it'll be in the day we schedule. We're normally doing labs. Yep.
Do we need to bring our board and meter?
No, you don't need a board, don't need a meter. It's all on the exam. It's not like I asked the opinion of a couple other professors who, if they've ever tried that, is making a circuit on a board a good idea for an exam. And the ones that have tried it said, no, that's not a good idea. It's a great concept. And if we had more time, perhaps, but in the time frame we have, no. So I'm not venturing out and doing that on this exam. And I've never done it on the final exam either.
I have a question, sir.
Yeah,
So for the exam, just to clarify, it is going to be a paper exam.
it is.
What is the number of questions for this exam?
That's a good question. I'd have to look it up. You know what? I did it over the weekend. I can't remember.
No worries. If you could
no,
just give an
just-
announcement or something when you do know the answer, that would be perfect.
Okay, I think I did a breakdown. Did I not put a breakdown on the announcements? Or did I do
It's
percentages?
possible. I'm not 100% sure. I haven't, to be completely honest, I was just looking to clarify verbally. I haven't actually taken a full look through myself.
Right, okay. Yeah, no, I don't have that document right in front of me. I've got,
Okay, that's okay.
but yeah, if you go on to the announcements, I break it down as to, I think I did it in percentages because I wanted to give you the amount of time what time to focus. And I can tell you, if you're kind of looking how to parcel up your time,
Yes.
there is a question that there's a similar thing we did on the last lab where you have a circuit and we change it. And I think I've done one variation on a theme like that. There's that, but there's one that I make a change to it and said, okay, it should be this, but it's not. And you've got to kind of look at the circuit to figure out why the circuit's not doing what it's supposed to do. So
Okay.
at any rate, that's why I'm showing all this because it's a key, it's a cornerstone skill set that you require in this trade.
Absolutely, and I appreciate that.
Yeah.
And just to clarify, as far as materials needed, it'll just be a calculator, a pencil, anything else?
Well, make sure you have the gray matter, that you haven't had too much to drink.
Fair enough. That's good. Okay, fair enough. Yeah, and I think if that's everything, then I have no more questions for you.
Yeah, now I will try to bring a spare calculator in case somebody's breaks down. So I don't want calculators floating all over the room. I'm gonna see if I can grab a couple. I might go out and buy a couple more just to make sure that if their battery dies, I don't
I have a
want you using
spare
your
that I
phone.
bring for every test as
Oh,
well, but obviously
yeah.
I won't. It's only one, so I won't.
Yeah, no, I've got that, but I've seen people grab their phone and start using their phone, and
Yeah.
according to the college policy, you're not supposed to do that.
No, you're not allowed to do that. Absolutely.
So,
Okay. Well, thank you very much. I appreciate that.
okay, enjoy the rest of your day, and we'll see
excuse
you
me,
on
sir.
what's today, Monday? So we'll see you
anything like that. I'm just gonna post something here on the, maybe make this a bit easier. So there is like a midterm review on Slate. I'm just gonna post it here. Let's add another page. Oh, and actually should say it's gonna be oh, sorry, hold on a second here. There we go. All right. So actually I gotta change because normally this motor stuff is at the end, so it's actually gonna be what's called your final exam review. So let me hide that. All right. Okay. And we'll go over like I said, we'll go over everything so there's no surprises. So again, I'll post it. I emailed everybody. Make sure that you're here on time. The room number is on Slate. I sent an email through Slate as well. I'll also oh sorry, hold on a sec. My
Professor, I have a question.
yeah.
Like, we need the code book also.
You can bring the code book. It is like they're not probably won't be like a lot of like code rules, but you can bring the code book. Maybe some questions you'll be able to answer, right? It's an open book test in that sense, but it's not going to be like super heavy on the code stuff. So, all right, let me go through. And let me just make sure. 1 second here. Yeah. Okay, so let me share. Sorry, my screen dipped out here. So share. All right. Okay, so we're gonna go through basically everything motors, right? And this is basically your review here. What's going to be on it? We'll go through some like kind of questions and everything like that, maybe that you can expect to see. There's going to be there's certainly going to be some multiple choice questions. There's definitely going to be like some drawings, right? You can maybe have to do some schematic drawing of sorts. But let's work through all that right now. So first of all, like first things I expect, those things here. Let's go through. Actually, let's go through the points here. 1 second. Sorry, I'm getting distracted because my screen keeps clocking out here. 1 second. Let me just. Right. There. Okay. So what's the volt like? And this is a review. So first of all, what's the voltages that we're using in our control panel? What is our like? What's the voltage that we've been using so far?
208.
120, 208, right? Like
Yeah,
these
208.
208 line to line. It's important to maybe understand the differences, right? Line 1, line 2, line 3. Right? Line to line is 208, any two, right? Okay. And those are marked like red, black, and blue, right? As we know. Okay, so line to lines 208. Line to neutral is going to be 120 volts. And line to ground is also 120 volts because hopefully, as you learned in residential, like your neutral and ground are actually connected together at a particular point in a service at the beginning of a service, right? So maybe like understanding those voltages. If I'm measuring line to line, what I would expect to get from measuring line to neutral, what I expect to get. It's gonna be like, again, it's gonna be some practical knowledge too. So let's go through. All right. So that covers that. What do I mean by clockwise and counterclockwise rotation? What do I mean there? Well, does it matter the order of the colors? Yes or no? Just Y or N maybe in the chat if you're not sure. The order of the colors matter? So this review is for you guys, not for me, right? So yeah, it does, right? Because the order affects the mechanical rotation. Basically, the order affects the rotating magnetic field. So if the rotating magnetic field changes, then then the direction of the motor is going to change, right? So that definitely has effect, right? So typically red, black, and blue, ideally we want clockwise rotation. But if we flip, how many wires do we need to change direction of this motor? How many wires? If I have a three-phase motor, how many wires I gotta change?
Only two.
Any two, just once, right? Just I can change red, blue, blue, and black, right? I just gotta change 2 wires, and I've changed I've changed everything, right? I've changed the direction of all these rotations. Gonna reverse it, and that's it. And we did that a couple ways. We did that with our forward reversing contactor, right? And we also did that with the drum switch. So that was 2 ways to change, right? All right. Okay, so identify measured voltage at different points of a circuit or schematic. And you probably need to draw some kind of simple schematic. Probably not anything as complicated as we did at the end. But if I'm going to draw a latch circuit, what's the first button going to be here? And what's the second button going to be? So the button at A, button at B, what's that going to be? This should be pretty. And is it not what is normally open or closed? Stop is going to be
Normally
And-
closed.
and yeah, NC, right? It's going to be normally open. Stop, start, right? And again, this stuff we've gone through before. What's going on here? Hold on a second. Let me just all right, so that's fine. Okay. Sorry, I just had to change this here. So stop, start. Okay, and then we have our coil, right? And the coil is the magnet, right? So if we have a contactor, the coil is the magnet, right? The coil